Okay, I think we can start. Welcome to the session today on XQuery performance and optimizations. I hope if there are more people coming that they will still be let in. My name is Michael Rees. I'm a program manager in the SQL Server Engine team. I joined Microsoft over 13 years ago with the intent of adding XML support in SQL Server. We did that over 2 releases in 2000 and 2005. And then we have done some small improvements since then, and there was nothing major done in SQL Server 2012 on the XML side. However, there is one feature that we are working on that will be coming soon. I can't say quite yet when, because it hasn't been decided yet, on the indexing front. So today, I will take you along on a dive pretty deep into XQuery and XML, how to basically do performance tuning, how to use XML in the database, and how to use XQuery in the database. How many of you have used XML in SQL Server? I hope the number is high, because this is going to be a 400 to 500 level deep dive. So I'm not expecting to do much introduction, except maybe give some best practices at the beginning. So the goal of the session is that at the end of the session, you will have an understanding of when and how to use XML in SQL Server and understand and correct common performance problems that we have seen in the wild with XML and XQuery. And please apologize my voice. That's like my 4th presentation at the conference, so I might be starting to lose it today. The session agenda is packed. So we are starting with the overview of when to use XML and when to store it in XML format versus relational format. We then talk a little bit about some general XML design optimizations, like when I design my XML document, how should it look like? Then we go into some general optimizations that are generally applicable, not just for XML, but for other large objects as well. And then we go and talk about the data type methods, how to use them best and how to make use of them in a way that you can improve performance, and how can we avoid some bad practices that people are doing in that space. Then we go into the actual XQuery optimization, like what do we do to write good XQueries versus bad XQueries, and how can indexing help us? And then we are basically going through the different index options. Towards the end, I'm going to talk a little bit about some interesting query optimization patterns that you can use to make your XQueries go faster. And then at the end, kind of as a teaser, I'm going to show the new selective XML index work that we are working on, give you a demo of it, and I hope that it will be available sometimes within probably the next 12 months or so. But I can't promise it yet. So let's kit up and scuba dive down into the depth of XML and XQuery. XML originally was designed as a markup language, as an extensible markup language, and has found adoption in basically 3 main scenarios that are relevant for the database people. The first one is that you're using as an exchange format between existing systems, so you need to be able to receive an XML message, marshal it back into your database, and have data inside your database participate in the data exchange. In addition, you also have XML being used in its original intended format as basically a document markup language, where you have different types of documents that you are describing in XML, and you want to store it in its entirety inside the document, inside the database. So you basically have mixed content, you have things like order is important, etc. And then last but not least, XML also has often been used as a way of managing and modeling semi-structured data. And nowadays, if you look at many of the NoSQL stores, they use either XML or JSON to achieve the same goal, to basically give you more flexibility in terms of what the data model is of the data that you're storing inside the database. In all of these cases, you want to be able to transport, store, and query the XML data inside a database. And so that's what we are focusing on, specifically the last 2, the storage and the query part. However, before I store XML in the database, there are a couple of considerations you have to do to figure out, do you want to store the XML as XML, or do you want to actually take the XML, decompose it into relational form, store it relationally, operate on it relationally, and then at the end potentially shape it back into XML form? The later part, that decomposition into relational, of course, will give you better performance because it's relational data, so it fits relational model. You should keep it in the relational model because there's 20 to 30 years of experience on how to make that go fast. So I came up with this decision tree here that gives you kind of a guidance on how to store your XML inside the database. The first question you should ask yourself is the relational data that you have really is the XML data really fitting the relational model? Is it basically just entities with a couple of fixed set of properties? And you know a priori which they are. If it's yes, then you use some of the mechanisms that we have to take the XML apart and basically put the data into relational form, store it there, run your relational queries, etc., and everybody's happy. If it doesn't fit the relational model, then the next question is the data semi-structured? Meaning, yeah, it's still relational, but I don't know a priori what are the fields, or there are lots of fields that might come and go, and it's a little bit more of a mess in that regard. It's not fully normalized. And so then if the answer to that is yes, then the recommendation is that you still take some of the structured parts, shred it into relational format, and then store the semi-structured aspects either in XML form, or if you know a priori what these semi-structured parts are, you now, since SQL Server 2008, can also use sparse columns to store them. So if there are no sparse, you basically put them into a sparse column. If the data structure is not semi-structured, then it's basically a document. So the answer to that should always be yes. And then the question becomes, well, do I query into the data? Because if I don't query into the data, I can store it as a var binary max. That's the most efficient way of storing my XML in the database if I don't need to actually look at it, and I don't need to parse it and make sure that it is actually XML. However, if I want to have any of the XML capabilities in SQL Server, of course, then I should store it as an XML data type. And then there are additional considerations to make, like which indices to define, and we will go into that a little bit in the presentation here. Another one is if I query into the XML with very frequent kind of query patterns, I might want to use something like property promotion, like using computed persistent columns, for example, or again through extraction mechanisms, move the data out into the relational space and do a relational lookup. That's kind of like pre-computing the query, so to speak. And now in the future, you will be able to use selective XML indices to promote these frequently queried fields out into an index and give you better query performance. Now also, if you want to search within the XML, you probably want to define a full text index on it, and that actually works. Our XML filters will give you the ability to index all the non-numeric attribute and element fields without indexing the tags in the full text index. Otherwise, if the XML is constrained by a schema, you might want to consider adding a schema collection to your XML data type. We'll talk about that later as well, a little bit in detail. And basically, it's okay if the validation cost is fine. And you might want to make use of the semantics that the schema gives you in addition. So just as a recap, how do we process the XML inside SQL Server? The XML comes in and there's an XML parser. The XML parser makes sure it's XML or the fragments of XML and creates a binary representation of the XML document itself. That gets stored inside our XML data type. So it's not the textual thing that you give us, but some binary transformed thing that is often smaller, but it's fully encoded in Unicode. Then optionally, you can have a schema collection that does some additional schema validation and also adds type information to the binary representation of your XML, which gives you additional semantical information about the data itself. Then you can run queries over it. Now the queries or updates, now actually they are not really running on the binary data, but what happens is every time I run a query, a table-to-valid function that we will see later in our query plans, etc., will be applied to create a node table. That internal node table is a relational table on which we run the XQuery using primarily relational operators, but preserving the XQuery semantics. Now, if you want to persist that, you create a primary XML index. And then you can define additionally 3 indices over the node table that give you additional performance benefits. And we go into that in more detail towards the end of the presentation. Now, in the future, you will also be able to have a selective XML index, which will then basically do the same thing, promoting the properties that we want out into what we call a white sparse table. And then you can, again, define secondary indices on top of that. Furthermore, in our XML processing, you can promote data out, either using OpenXML or the nodes method in the database into row set and have for XML to get the data back into XML shape. So that's kind of what we have. So if you look at the general impact in terms of what you do when you use your data, there are a couple of things that you have to consider regardless of whether you're using XML or specifically using XML, but it's not like semantic implied, as it has nothing to do with the query. First one is concurrency control. If you are doing an XML index, then an XML index will have a lot of rows per XML document, because each node in the XML document will have its own row. So that means that if you do a query or an update on an XML instance, you will lock the original row in the table. But that can lead to a lot of rows being locked inside your index. Now, often that's fine, but once in a while, when you have really skewed data with lots of rows with small XML documents and one row with like a really huge XML document, it can happen that there is a row lock escalation happening on the index, which means suddenly, instead of just locking the rows that are relevant in the index, the whole index gets locked because it's an internal table. So in that case, you might want to do snapshot isolation to reduce the locks and lock contention if that's possible. Also, transaction logs. If you do bulk inserting into XML indices, it might actually fill up the transaction log because it's a hidden extended table, so to speak. So therefore, the recommendation is that we delay the creation of the XML index and use a simple recovery model if that's going to be a problem. Also, the general recommendation is pre-allocate your database file if you know how big it's going to be instead of having it dynamically grow, because that adds to the insertion cost. And also place the log file on a different disk. I mean, that's standard usage anyway. Also, an XML document at the storage engine layer is nothing else than a large binary blob. And so, therefore, the in-of-row and out-of-row option that you have on var binary max, etc., you also have on the XML data type. So that means if you, for example, often, if you have relational data and XML data, and you often query the relational data, you want to be able to potentially just have the XML out of row because you might not be interested in looking at the XML every time you fetch a page. On the other hand, if you always look at the XML and the XML documents are small and might fit into the 8K limit, at that point in time you might want to have it inside the row as well. So you have the choice here. Also, another interesting thing is, as we will see later, the primary XML index will have a clustered index on it itself. And so that means if I do an insertion there, I have to be careful in terms of what the primary key of my table is. Because if it's a primary key that is not increasing every time you add a new instance, you might have additional non-linear update costs if you do insertions into the table. So that's, again, something not necessarily specific to XML. It's just how primary cluster keys work. And so a recommendation here is, if you use a big int identity column, for example, that should help you with that aspect. So now let's go and look a little bit more into detail about the XML modeling. So many people come to me and ask, well, XML have attributes and elements. What should I use to model my data? And my answer normally is, well, it depends. There are certain benefits of element centricity, such as that you can have complex objects. You can have more than one property, like more than one phone number, for example. On the other hand, the performance on attributes is often better because it's just a single node attribute, so we kind of know it's only once there, and et cetera, et cetera. So either one of those is fine, but either one has certain implications on how you will later write your queries, and we will get into that when we look at the query expressions. Another thing is, and that's more of a pet peeve of mine, and the modeling question is, XML is an extensible markup format. So you can create a new customer element, and you can create a name, and you can create, I don't know, an order element, etc. There is no need to go and do things like entity type equals customer, property type equals name. Many people that come out of a relational world, they still want to have like this kind of, I want to know what my element name is, but no, you don't really want to. You just want to model the data. And having that kind of additional gook there is actually problematic. Because what it actually does is it adds lots of overhead for path expression. And now if you want to look for a customer in the first modeling, you will have to write a predicate instead of just being able to do a structural lookup along the path. So it's better to model this as customer name Joe instead of entity type customer property type name with a value of Joe. Also, wrapper elements, often people think that they have to say orders and then have all the orders inside. It depends a little bit on the embedding on the client-side app here, whether that makes sense or not. But from a purely query point of view, it just adds additional path expressions. So it just makes it slightly less efficient. I would recommend these order wrapper elements primarily if you have additional collection level properties on that you want to capture. Then, should we use an XML schema collection or not? First, I would like to say you can run any query that you can run without the schema collection being defined. So all your XQuery expressions work even if you don't have a schema. Also, the atomic values that you have are always weakly typed strings if you don't have a schema. So by adding a schema, you will actually add additional type information so you get semantics on it. If you have no schema, you obviously don't have an overhead of a schema validation or any issues with revalidating when you evolve your schema or your data. On the other hand, the schema actually gives you that structural information. It tells you that there is exactly one element here that is of type integer, and you will get integer semantics. So there is both benefits also to have that. The static typing also can give you early error discovery, etc., while you're writing your query, which you don't get when you are not having an index, not having a schema collection specified. Also, the semantic information can actually help you with giving better performance, and we'll take a look at that as well. So now let's look at the XQuery methods and how to use them. Just as a recap, there are 4 methods for querying and 1 for modification. The 3 that you see here is query, takes an XML document, applies an XQuery, gives me an XML document back. Exists, takes an XML document, takes a XQuery expression, and will give me back 1 if the XQuery expression results in something, and gives me 0 if nothing is there. And the value method is basically like a cast out of the XML world into the SQL world. It basically takes an XQuery expression and the T-SQL type and will cast the result of the XQuery expression into the T-SQL type system, so you can then do relational processing on it. There are certain limitations here that are on the slide. I'm not going to go into those in detail in the presentation here. Then finally, we have the nodes method. The nodes method is kind of for us to give you the ability to take complex XML documents that potentially represent a set of things and create a table out of it. So what it does is it takes an XQuery expression, and then for each node that the XQuery expression generates, it will basically create a row that then points to that node. And then you can use the value method and the query method on the context item in the select clause to propagate the values out. And you will see those queries during the presentation in the demos later on. Also, an important aspect is this nodes method is basically appearing as a table-valued function in the query plan if there is no index present. If there is an index present, obviously, it's not going to be a TVF. Then we already have the data shredded out into an index. Furthermore, there are 2 built-in functions that we provide that give you access to access relational data in the context of XQuery. The first one is the ability to refer to a variable or parameter, and the second one is to basically provide you access to another column in another table. And that gives you the ability to do joins. And we'll talk a little bit about, there are basically now 2 ways of doing joins. One way is doing this. You get the column that you want to join on into the XQuery context. The other one is you use the value method to move the data out into the into the SQL context and then do the join in the relational context. They are both semantic implications, like, for example, string comparison in XQuery is always a binary Unicode collation, while if you're going into T-SQL, it's whatever collation you have for your database. So there are some differences here, but often it's primarily performance and style. So there are some restrictions here, again, on these around that you can't have an XML data type for these or any of the deprecated types like datetime, text, and text image, etc. So now let's switch over and take a look at the demo here. Okay, so for this purpose, I have 4 databases. All these databases are containing the same data. It's basically 20,000 rows of objects that look like this, and then 3 objects that are really large to kind of add some skew. What it is it's a document that contains some customer information with an ID attribute, some elements underneath about name, street, etc. And then it has a set of orders, like order ID 1 and 2 here. And then it has some mixed content nodes, like this one says big customer of Giggles currently gets Wiggles from competitor Acme. And then there's some additional markup in between to make it a little bit look like XML. So that's kind of the data that we are storing. Now, at the moment, the data is all in XML. So the column basically has an ID column and an XML column. Now, these 4 databases then differ in basically the way that they have either a type associated, a schema collection associated with it that describes that format, and or whether they have a primary index already defined on it. So here, for example, I ran this query earlier that basically shows you 2 of the databases. The one that has, that has no schema associated with it, but what do you call it, the primary index, and one that has a schema associated with it but no primary index. And the interesting part here is the size of the data. So if we scroll over a little bit to make this a little bit more visible, you will notice that the data that we have at the moment is about 15 megabytes. So it's not that big, but it's big enough to show you the differences. And that's in the untyped case. Now, if you look at the typed case actually adds more data, so it's 36 megabytes. That's because we now have more information about what type it is, etc. So there's more annotations in the binary blob stored. Sometimes it might be less. So that size relationship between the untyped and the typed one could also be the other way around, depending on exactly what the information is that we are capturing with the schema. The important aspect here, and probably everybody who has been using XML indices has noticed, is that the primary XML index here is 3 times the size of your core data. Now, with 15 megabytes, that's not a big deal. But we had customers that had terabytes of data. So you have 4 terabytes of XML data. And now you need maybe 4 times as much space for the index. I think I'm going to buy EMC and NetApp and Fusion.io stock, if that's the case. So basically, that's a little bit of an adoption blocker right here. One of the problems that we have, the primary XML index allows us to query into everything, but at the cost of using a lot of space. And so that's something that we are going to address, by the way, with the selective XML index. But this is important to know that both this might be a problem going forwards if you're using the index, but it also, there is some help on the way. The interesting part is actually if I switch over to the one where I have a schema associated and I rerun the query, hopefully it goes fast. Sometimes these queries with the DMV here take a minute or 2. You will notice that the index with the schema information is actually going to be smaller. So if you move over here, the primary XML index here is only 33.5 megabytes, which is about 10 megabytes smaller than the other primary index. In this case, however, since there's more data in the document case, it kind of gets evened out. So this is the data that I'm going to use in my query, just show you here. Basically, we have about 20,000 rows for the XML documents, and then I have some contact info that has additional rows, which just adds phone numbers for a few of those, so I can do some nice joins. Now let's switch back. So what I'm doing now is, in the next couple of slides, I will show you bad patterns, talk about what are the good patterns, and then I will switch back to the demos to show you actually how they relate and how they actually execute, so you can get a feel of the performance improvements. So the first one, and this is really everybody, I don't know, how many of you have written that type of query? Where you basically say, I need to get something out of my XML into SQL, and I need to have it as an integer. So I take the query method, I cast it into a string, and then I cast it into my final type. I hope nobody, but if somebody did it, don't be afraid. Lots of people do that. And every time I get one of these cases, I would get $1. I will probably be retired. So the thing here is really, this is not the way to write it. And why is it not the way to write it? Well, because we have actually provided you with a value method that does exactly that. Not only does it do exactly that, but it actually gives you the right string representation too, if you want to extract a string that has an ampersand in it, for example. So the way to write this is basically by using the value method. Also shorter, you have to type less. Another one is that I see people, especially using the nodes method, do a nodes method, and then they have a node. And then they say node.query dot. And then they say value. The query dot thing does two things. One thing is, the node here is just a pointer into my XML document. So what this does is, it actually extracts the subtree of the thing that I have, creates a new XML instance, and then on that, I actually then apply that extraction. So this is very inefficient, unless you want that copy semantics there. So the right way of doing it is, well, you already have the node context item. You can do value method directly on it. There's no need to actually do that. So let's go and show that on the query side, which is, so I set statistics on, so we should be able to see it. We have the query plans on, so we can see that as well. So let's do the first query. So this is a query here that does the two things that I just mentioned. It's casting over XQuery several times, potentially, to get to my SQL type. And it's doing that query thing with the value method. This time it's doing it the other way around by saying value dot. So if I run this query here, oops, I'm in the wrong database here. Let me quickly, well, even if I'm in this database, it takes a long time to run. But let me quickly change the database here to the one that I was hoping to show you, which is the one without an index and without a schema. So the query is still running. It's probably taking about 10 seconds to run, so let's wait. So it's done now, 10 seconds, as you can see down here. Let me zoom in quickly. Oops, the zoom it hasn't started yet. Let me quickly start zoom it for you guys. Don't you love Windows if it's having problems finding things? Let's do that later. I think you believe me. I can also show it here under the messages if the statistics is turned on, which apparently it hasn't. So it's 10 seconds. Now let's run the thing in the way that we want to run it. So this time, I'm basically using the value method directly, no casts, and no query in between. Now, remember, this query doesn't have an index. It goes over all the data, but I'm now done in 4 seconds, or to be exact, in 3.8 seconds instead of the 10 seconds earlier. So writing the query in the right way, using the methods correctly, definitely is important. Now let's go back and look at another case. One thing that we did was we actually have an optimization that if you take the value method inside your select clause and put them next to each other with the same XML variable or pointer as the context node, we will be able to do some optimizations underneath the covers. And by doing those optimizations, it will give us the ability to basically give you better performance. Now, however, there are a couple of requirements on what the method inside the value method or the query expression inside the value method can look like. So it has to be a simple path expression with no child node or attribute access explicit, do not contain wildcard, doesn't have a predicate on it, etc., etc. And once you get that, and the path expression infers statically a singleton, then we can push it into the path, into our extraction mechanism. Now, there are two additional things. One is the singleton can be statically inferred by either having a schema collection and the document constraint on an XML, or by using relative path expressions inside a method that is provided by the nodes method. And it requires the XML index to be present. So let me show you that as well. So this time I'm going to my database that has both a schema and has a primary key, a primary XML index. So as you can see now in the value method, I can just say first name and last name without putting the bracket 1 there. But as you notice, I have here my C's and O's all interspersed with each other. So let's run this query. And so what the query does is, while it's running, is it basically gets me the customers and their order information out. So I basically get one row per each order for the customer. So the query is still running. Probably takes a few seconds here. So it's done. So let's see how fast it went. And if you look down here, it basically took about 4 seconds. Now let's just rewrite the query here. And now if you notice, I have all the C values and the O values next to each other. But otherwise, the query is exactly the same. So let me select this and execute this and see how fast we are this time. It still takes a while because I'm basically going across all the data, do a cross-apply, and get about 40,000 rows back. But you noticed that I'm now done in 7 seconds instead of the earlier 10. So as you can see, we are actually making use of that optimization. And if you combine all of these things, you're actually going to get quite a bit of a boost in your performance. Another thing is that you can, as I mentioned earlier, you have 2 ways of doing joins, using the exist method and using the value method. And basically, it depends which one of those to use depending on what indices you have available. If you have a primary XML index with a secondary XML index defined on that, then it actually makes sense to use the exist method, importing the relational data into your XQuery context. If not, then you're probably faster using the value method doing the join in the relational context. If you have to choose whether you actually want to define an index or not, then using the index is actually going to be faster. So using the exist with an index should be faster than not having an index and using the value method. So if we have an index, a secondary index on the primary XML index, then this is a bad pattern, and this is a good pattern by moving the thing inside. Also, as I mentioned earlier, the value method is otherwise more efficient, comparatively speaking, but adding an index will make it always faster. Also, there are some issues with the nodes method. SQL, per se, has some costing problems with table-valued functions that you put inside a from clause. Basically, nodes without the XML index is a table-valued function. This leads to bad cardinality estimates that can lead to bad plans, because basically, if I write a query like this, I say, select my values from customers' nodes, where customer ID, blah, blah, blah. The nodes method will be basically estimated to cost about 10,000 rows. That's kind of fixed. We're doing some additional optimizations that we'll get to later, but that's basically what it does. Now, if I do a join here with another table, like the customer table, now suddenly it might actually flip around it will flip around my experience, and it will give me a really bad join where basically the outer join loop is going to be much more costly than the inner join loop, even though I might only have 4 nodes in the XML. So it's important that you can kind of influence that. Now, one way to influence that is if you know that you, for example, only have a single wrapper document here called docx, then you can actually put it in like this, cross-apply, and in this case, since we know doc bracket 1 is always a single element, we actually can give that thing a cardinality of 1 in the query optimizer plan statistics. And what it will happen is that maybe we get a better plan that way. Another way, what I normally recommend is if you have a parameter that is XML, and you want to join the parameter with your XML inside, with your relational data, and you use a nodes method to get the XML data shredded into relational form, then you should actually not have the XML nodes method in the join expression itself. What you should do is you should put it into a temp table, and then afterwards use the temp table for doing the join. That way, the temp table actually has much better statistics, and you will normally get much better query performance because now you're actually having statistics that are more accurate, and the query plan will probably be much better than otherwise. So another thing is methods are not cheap. It's not like just an addition. So you should avoid having them invoked more than once. So an example here, if I have a case statement, and I do the first one is if there is some condition on the value expression, then do one thing, otherwise do invoke the value expression again. It's obviously not what you want. So what you should do is you actually should move it down into a subselect, and then that will only get executed once. To show you what impact on performance that has, I'm showing you again a query expression here. So this one is having a few case statements here, about 4 or 5. And it's basically always checking on the value that we extract and then do something with it. So let's run this query. As you can see, it takes a few seconds as well. Let's see what the message says here. It's about 9 seconds. Now let's run the same query, but actually move the XQuery shredding into a subquery. Of course, we could also use a common table expression using a with clause. Now when I run this query, it goes from 9 seconds down to less than 2 seconds. Or about 2 seconds. So as you can see, we're getting almost a factor of 4 performance improvements by just avoiding that double execution. Now let's switch back again and look at the next thing, and that is XQuery optimization. So what I've shown you now so far is, without regard to how you write your XQuery, how should you use your methods? Now let's look at how to actually write the XQueries. To introduce that, I would like to first give you an overview of how we actually compile and combine our XQuery and SQL expressions. So if I have a SQL statement, it gets parsed by the SQL parser. The SQL parser does some static analysis, algebrizes it into some internal tree. And every time it sees an XML method, like a query or a value method or a nodes method, it will call out to the XQuery parser, and then the XQuery parser will do its parsing. It will do static analysis, optionally taking a schema collection into account, and algebraize. And then during that compilation phase, these two algebrization trees, or many algebrization trees, will basically be combined, and then you have your query. And when you execute, you will basically execute it while making use of the indices, etc., that might have been specified and are known at compile time. So this is basically how this works. XQuery is not run at runtime. It's algebraized and compiled like your SQL query. In order to be able to do that, our XQuery expressions are primarily translated into these relational expressions against that node table I mentioned earlier. However, in order to be able to create the node table, of course, we have to have an expression that takes the XML and creates that, which is the table-valued functional XML reader UDF with XPath filter. That's how it appears normally inside your query window. This is always used if no XML index is present, and it basically creates that node table inside the flow of your query. We can push multiple paths into that to optimize it. Like I mentioned earlier, basically that value method optimization is kind of doing something similar as well. But we already talked about the cardinality. It's always 10,000 rows, although if we push some of the paths in some circumstances, we can reduce the number a little bit. Now, the node table looks like this. You have the ID, which is the ID of the node, which is basically a hierarchy ID. So it tells me exactly where in the tree it does, and it allows me to cluster nodes that belong together close to each other because it's basically containment. And we have title, like the name of the element, what type is it an element, an attribute, what type it is, if there is a schema present, what is the value, and a very important aspect is that HID, which is basically the inverted path expression, which allows us then to do very quick lookups based on path expressions to find the necessary nodes that we are looking for. In addition, we added a few other algebraizer components. One is the UDX, and the serializer UDX, XQuery string UDX, and XQuery data UDX are all kind of the same. What they're doing is they take a node and extract from the node the textual value. Now, in many cases, this will actually be translated into just a field lookup. If I go back here, often it's just a field lookup on that value field, so then they disappear from the tree. But sometimes they have to go and do aggregations of subtrees, and then they appear in the plan, and that normally is a bad sign. That means that you have some places to optimize. There's also a check UDX here that I'm not going to go into. Now, these things are visible in the SSMS property window. If you look at the query plan, we'll see that later. So that means one of the things we want to do is we want to basically avoid having these UDXs appear. So let me now give you a little bit of an introduction into what XQuery calls atomization of nodes. Anytime you refer to an attribute or an element, and you want to use it as a scalar value, like the age of a person or so, underneath the covers in XQuery, something like atomization happens. It's like unboxing. It's unpacking the value out of that element or attribute node. Now, if you do that, then basically you can kind of look at it, and there's a function called data that basically does that explicitly. So you can kind of rewrite all of these accesses explicitly. So that looks like this. Now, the same goes for atomic typed elements. The same thing happens. If you have untyped or mixed element content, then what happens is that we are actually taking the string value of that node. Now, the string value of that node is defined as basically the concatenations of all textual leaf nodes underneath the tree of that node. And that's a complex aggregation. Now, if I look at how this actually gets translated into my XQuery node table, the first two are very simple. If I have an atomic typed element or an attribute, I'm actually looking just at that value field in my index. If I have an untyped element or I have a mixed content typed element, then I don't know that there is a value field. I don't know how many nodes there are underneath myself. So I always have I have actually an extra row in my index that will have the value 42 for the age, and I will have to do that aggregation all the time. And that adds this UDX in the query plan. We'll see that in a minute. So if I only have a single text node, and I know that, even though I don't have a schema, I can write the same query expression as age give me text equals 42. Now, in that case, I basically avoid the aggregation because I just access the node itself directly that contains the value. And so, therefore, this expression is similar to the ones above, can be served directly out of the index again without the need for doing that UDX. And the same holds for my value method. Like anything I set up here for this predicate, is the same here. Person/age integer is exactly the same issue. So this is just saying that this string there basically prohibits index use. So let's take a look at this over here. So you remember the query that I had early on? And let me go back into my untyped environment here. So you remember this query here. I was saying, give me first name, last name, etc. When I execute this, it's taking about 9 seconds. Let's be precise here. Yeah, 9 seconds. And if you look at the query plan here, then first thing you see is that query plan of XQuery expressions is always quite complex. Let me quickly zoom out. Let me zoom here so that it actually fits. And you can see it kind of looks really ugly. Now let's move in again. Let's see, zoom in. A couple of zoom ins here. And my apologies for not having a scrolling mouse, which would make that much easier. So, and as you can see, we zoom in into something that is quite interesting. There is this XML UDX here. And if you go and click on the property, we would see that this is a data UDX or a string UDX. And what this does is it's basically doing that aggregation. If we can get rid of that, our query is going to get faster. So let's get rid of that by doing the trick of saying first name / text, bracket 1. Now if I run this query, remember we were 9 seconds earlier. Let's see how long it takes this time. Now we are done in 6 seconds. So we are 50% faster. The execution plan looks simpler too, because now these UDXs are gone over here. There's no UDX in here anymore. So as you can see, writing the XQuery with understanding how things operate underneath the covers, unfortunately, is still needed, unlike in certain relational database systems where you don't have to do the join order explicitly anymore. And that's primarily a sign of the status where the state of the world was when we implemented that. The interesting part is with the selective XML index that I will mention later, you actually don't have to do that workaround anymore, or that query formulation anymore. So now another thing is the casting of values. XQuery has both an untyped and a typed world. In the untyped world, you basically, every time you do a comparison, you will actually take the value and type it into the comparison type. So for example, here, I have an untyped attribute age. Now, I compare it against a number, 42, an integer number, a decimal number. So what will happen underneath the covers is that this gets cast into decimal. If I have an untyped text node, the same thing happens. If I have a typed element that happens to have another type than my comparator, then there are some type promotion rules that XQuery has that, for example, will make this integer to float comparison into a floating point comparison. Now, all these casting is expensive and can prohibit index lookup. So you want to avoid that. So how do we do that? It's the following. We should use the appropriate type for comparisons. If I have untyped data and I do equality comparison, it's probably okay to use a string. So instead of saying age equals 42, say age equals string 42. Or use a schema to declare the type, if that's important, like if you do greater than or less than comparison, where string ordering is different than numeric ordering. So let me quickly show you that as well. And now let me scroll back to the place where we were. So here I have an example, again on my untyped documents, where I basically have an exist query where I say, give me back all the documents where I have a customer with an order where the years equals 2000. Now this doesn't have a schema on it, so this comparison against an integer will cast the internal string value into a number so that I can get the corresponding comparison. So if I run this query is a little bit faster than the queries that we have seen so far. And you will notice it's about 400 milliseconds. Now, let's do the same, but since the comparison is basically a string and can lead to the same result, I use a string here. And I run this query. And again, the result is there, but instead of 400 milliseconds, I'm down to 300 milliseconds. So we are just saving money by not having to do the cost and by being able to actually do the comparison directly. Another thing is, you have seen that HID that I use in that node table, and that will get persisted in the index. This gives me, the longer that is in my query, the more selective will be my query expression on my index. So optimizing, maximizing that XPath expression is important. So there are a couple of points there. For example, if I have a single path that is more efficient than doing a twig path, which basically means I do things like /a where b/c equals something, that's a twig path. So if I can avoid that, then that's good. I should be able to try to avoid predicates in the middle of path expressions because every one of those introduces a twig. So in this case, for example, I say book ISBN equals author first name Davis. In that case, it might be better if I break that off into two queries and then basically combine them in the relational context. Another thing is moving ordinals to the end of path expressions that will avoid twigging. So for example, I say /A1/B1. If I know that there is always a B within an A, then I can basically say that this is the same as /A/B1. However, you have to be very careful here about the semantics because none of these are equivalent. The first one says, give me the first A, and then give me the first B of the first A. So if their first A doesn't have a B, it's empty, otherwise it's a B. The second one says, give me the first B out of my A's. So if the first A doesn't have a B, then you will just go to the next A and get that B. So it's a different result. And the last one basically says, for every A, give me the first B. And then another thing is, if you write book, and you know that an attribute is always 1, so these are equivalent, these two expressions, you still want to make sure that you're putting the bracket 1 outside because it makes the path look longer. We are not going to break it up into two paths. And specifically, the best place to use that is if you have an exist method. Because in an exist method, you don't really care whether you find the A that contains a B with value C or whether you find the B within an A that has the value C. Because you don't care about the node, you only care about its presence. So that means if you have something like book subject where the text equals security, you can rewrite that into book subject text equals security. And your plan will get easier, simpler, and you will get better performance. So let's take a look at that as well. Here I have a typed environment. Just go in that for a second. And what I do here is I basically say, find me again all the documents where the order has a year between 2000 and 2010. So if I run this, I will get this executed in about 600 milliseconds. Let's look at the plan to see how the plan looks. So you will see the plan has a couple of clustered index seeks that basically access the primary XML index and does a couple of complex stuff here. Now I can rewrite that into a query that looks like this. Find me all the documents where the year of an order within a customer is between 2000 and 2010. It's exactly the same semantics. So if I run this query, the result time is going to be twice as fast. And if you look at the plan is much simpler. So that means that if you use the right kind of path lengthening, you avoid these twig queries, which avoids join in the paths, in the query execution plan, which then makes your query go faster, of course. And this is, of course, a very specific example because I obviously optimized it for show effect. So here's the example with the and in between. Now, the important aspect is that this and unfortunately doesn't work with the or predicate, because it's kind of it gives me back too many results normally. Another thing is inside XQuery that some of the operators that we have are unfortunately not very efficient. So one thing that you want to avoid is you want to avoid inefficient operators. How many of you have used SQL Server 2000 with the OpenXML method? There were some issues with the path access there. That basically, if you added a path access, it became very slow. We fixed that in 2005. Unfortunately, we introduced another performance issue with the path access in 2005 on the nodes method. And I'm just showing you how you can work around that. So if you write something like this, where you have a path expression inside the value method there, so you get my orders, and you get the customer ID and the order ID. This is what I would write if I would be an XQuery person and a SQL person and come to it from beginning. But that's not the best way of writing it. It's better to write it using forward chaining, meaning I get myself my customer, I extract my ID from the customer element, I do a further cross-apply relative to the customers to the orders, and then get my order ID value out of that. Exactly the same result. Performance is night and day. Let me show you that as well. So let me go back to this database here. And so this is basically taking some customer order data plus some information from my customer using the parent access. If I run this query, it's taking a while. It's done now, so let's see. What is the time? Time is 12 seconds plus. Now let's run the same query, but this time I have this forward chaining with the orders and the customers in different nodes. And this time the query should be done a little bit faster. As you can see now, I'm done in like about 8 seconds. So again, about a 50% performance increase by just writing the query slightly differently. There are other inefficient operations, like if you're lazy and say /A//B, we are not able to use that HID entry. So basically make sure that you have // never in the middle of a path expression if you know what the data structure looks like. Don't be lazy, basically. You can be lazy by putting / at the beginning, though, because our HID index allows us to do a // lookup with a prefix lookup. Another thing is that when you do XQuery construction inside your query method, that's often less performant than decomposing your XML and use for XML to recompose it. So, for example, if I want to add my some information out of my relational table into an XML, so I basically do this construction here, then, yeah, that's not as good as writing something like a for XML path query. Let me show you that as well. So this is basically a query that does the first thing with the XQuery method. Takes about 200 milliseconds. If I do the same thing, but I do a for XML, and it's a little bit more complex a query, but actually the result should be faster. It's now 100 milliseconds. So now that I have talked about what you can do with XQuery expressions, let's take a closer look at the indices here. So when I create an XML index, I have the ability to create that on the XML column. Then I can create secondary indices as well on that. When I create it, an XML primary index will always be created single-threadedly, unfortunately at the moment, and multi-threaded for the secondary XML indices. The primary XML index will always be used if it's present, so it's an algebraizer decision and not a cost-based decision. The result can be directly served out of the index, so you don't have to go and deconstruct your XML document to find the nodes that you're interested in. The secondary indices will always be considered based on cost and statistics. So that one is not done by the algebraizer, but by the query processor. In terms of maintenance, primary and secondary indices will be efficiently maintained. So if you do an update, we only update the part of the index that needs to be updated. We don't recreate it fully. However, there is no online index rebuild. And if you have the cluster key issue, then that might lead to some non-linear maintenance cost. Also, if you have a schema associated with it and you do a change, the schema will validate across the whole document, which will be adding additional cost. So let's look at an example. Here we have an example index that basically contains some XML document with some attributes and elements, some mixed content there, like, for example, all right-thinking people love tree frogs. And let's put that into the index. So if I do that, this is kind of how the index looks like. On the front side here, you see the primary XML index. This is the primary key. That goes back to your base table. So this is kind of the way of us tying the nodes back to the documents that we have, to the rows that we have. Here are the hierarchy IDs, which are basically the XIDs that describe where we find the node inside the document. These two, the primary key from the base table plus this, create the primary cluster key for this internal node table that represents the index. Then we have the tag, node ID, type ID, similar to what we had in the table valid function, of course, and also the values and the HID. Now, with the values, there's an interesting point to make. If you look at this document, we are actually assuming that there's a schema present. So things like, for example, the element title 131 there is actually having the value associated with the element. And that's good. But if we would not have a schema, then there would be a null, and there would be another row similar to this row, which then has a text node underneath, because we don't know that it's a single value. We have to be prepared for it having to have all kinds of content. So that's kind of the difference here. So then the element will be null and not like this, and give us not the ability to just look up the value method. And then we have the HID, which is basically the ability to find something based on the path that we have mentioned a few times earlier. Then when we have secondary indices, what happens is basically each one of these rows get expanded into these multiple rows inside my index. And now I have the ability to specify 3 secondary indices. The first one is the value index. What this takes is it basically indexes off the value. So if I have a value, I can find what the path is, or I can find my primary key and node ID as well. And of course, these are covering indices, so that means that if I have the value and the path, I can find the node very quickly. Second one of those is the property index. Given the primary key of my base table and potentially the path and the value, I can find the node. Now, this is very interesting because that means if I have a relational index that already basically narrowed it down to a few primary keys, then I can use that index to basically join it and get better performance. And I will show that an example towards the end. And then last but not least, it's the path index that basically says for any path, I can find the value and the node. So let me show you that quickly. Let me jump over these queries here. Some extra bonuses. By the way, all these queries will be available for you to basically play around with later. So in this case, for example, I have to connect to my right database. In this case, for example, I have basically the query that we have seen before. Now, if I look at the execution plan here, this is taking the primary clustered key, so it's taking the pk XML doc blah blah blah. So that's my primary XML key index. Now let's say I create a path index because I have a long path there. And let's just make sure that we see how fast it was before I do that. So it was taking 200 milliseconds. So now let's create that index here. And now let's rerun this query. Now the query is done in 100 milliseconds. And if you look at the query plan, now the index here, oops, it seems to be not the index that I was expecting. So I was assuming that I see it. The statistics haven't been updated yet. So once the statistics are updated, it will use the other index. Unfortunately, that hasn't been the case yet. So what I can also do is I can use now the primary XML index and create a property index in addition to the previous index. And that one we will use later when we talk about some of the query patterns. So the takeaway is use the primary XML index when you have lots of XQueries. Use the value method if you have highly selective predicates with values in them. And use the path expression if you have lots of long path expressions, assuming the statistics are updated. And otherwise, if you have already a relational index or a full text index that already give you a result, use the property index to get that perform well. I mentioned property promotion. So you can do property promotion to get the ability to promote something out of the XML document and put it into a relational document. However, and then, for example, you can define a relational index on that to get fast lookup on it. However, one of the caveats is you have to basically embed your XQuery expression inside a user-defined function and then have to use that user-defined function to do the lookup. You can't use it just using XQuery because the query optimizer doesn't know how to look into these UDFs. And it doesn't allow me to use an arbitrary complex expression. It has to be a UDF expression to do that persistent column thing. And there is also another caveat, and that's a general one with persistent computed columns based on a UDF. There are currently no parallel plans on that. And so there might be a trade-off that you have to look at in this context as well. So now let me show you quickly how to use full text indexes and the property index to get a better plan. So for example, if you have an XQuery that contains a contains expression, and you want to find something that has, for example, the titles that contain optimization as a word inside the title. Now, the contains expression in XQuery is not a full text contains. It's a substring contains. But if your substring happens to be a word, then you can actually improve that performance of this expression by adding a full text index, do a contains on that word, which gives you a pre-step filter, which basically reduces the candidate documents to a much smaller candidate set on which you then do your XQuery exist expression. So let me show you that quickly. So what I have here is I have this expression that does the contain strings find me the snoozies. And if I look at now the plan here, you will notice that the plan is basically using the primary XML index, and that's about it. There's a clustered index here as well. So if I go back now and run the same query with a full text predicate, I have created a full text index on that column as well. And I run this. Now the plan is basically using the full text index here. And it's going to be faster than before. In this case, it took 3 seconds to compile, but it took less than 100 milliseconds to actually execute. While previously, it was taking longer. So let's just write that again, because I don't think I've shown it to you. You see, without the full text index, it's taking over a second. OK, for the last 5 minutes, let me quickly talk a little bit about the future, what we are going to have, hopefully, within a year from now. It's already running on my machine. It's just waiting to find the release vehicle, so to speak. We want to be able to give you an ability to have a much smaller index experience. So what we are giving you is now the ability to map specific XML nodes to a single wide relational table that gives you a much smaller footprint and still gives you the ability to support most of the XQuery and SQL comparisons that you have with our XQuery methods. It is not a cost-based index. So like the primary XML index, it will get chosen. if you have both a selective XML index, or SXI as we call it, and the primary XML index, or PXI as we call it, then the SXI will be taken first. Again, the same thing is as in the PXI. It is single-threaded and offline in the way that it's created. And you can define secondary indices on it that are giving you more performance, because it's basically a filtered index on each one of these promoted columns, making sure that it's not null, which gives you more performance if you have lots of semi-structured data in that index. It's also supported, of course, as a new class of index, so you will be able to use all the tools. This is how the syntax looks like. Basically, you have two types of flavors. The first flavor is that you want to optimize XQuery expressions, in which case you basically use either the path without any additional thing, or you can use optimization hints like saying, well, this is actually a string and it's a max length of 25, so therefore we actually map it down to nvarchar 25 instead of nvarchar max. Or it's a double and it's a singleton, so I know that there's exactly always one D within every B, so I can make certain optimizations again. Or, and these are all mapped then into XQuery expressions inside value methods, node methods, and query methods. Or I use it for value method comparison, in which case I actually, in the index, define that this path is going to be a SQL float or a SQL varchar. And then it will be stored that way and give me that corresponding match. Each one of these paths will get a name. And then these names can be used on secondary indices to define that index. Let me just show you quickly how that looks like. So I'm connected now to a different database containing the same data. And this is probably a query that you have seen before. It basically just extracts some information, first name, last name, out of my documents, where the value is equals to contact ID. So if I run this, it's going to take a few time. And of course, again, statistics wasn't set. So let me do that quickly. So I'm running this, and the result time was about 1.9 seconds. So it's about 2 seconds. And now I can optimize that further by basically using my value strict with the /text. But with the XSI later, that's actually not necessary anymore. So if I look at with the /text, I'm seeing now 1.5 seconds, so I gained about 25%. Now let's create a selective XML index. What I do here is now I basically, for each one of these methods, path expressions, I do create an index entry. For the internal nodes, like /doc/customer, which I don't actually need the value, just the presence or absence of the node, I can give a hint that I'm only interested in managing the presence or absence of the node in the index and not its actual value. So I basically create that index now. And now I basically rerun the same queries above. Let's run the first one here. That used to be the less efficient one because I wasn't having /text there. Now the query is already executed. Let's see how long it took. And you will notice now I'm less than a second. But not only that, if we look and compare the index size, I'm running my ugly big query again here that hopefully doesn't take too long. You will notice that now the index size is actually much less. It's going to be a percentage of the original data and not a factor of X anymore. So over here you see the XML index in row data here is now 2 megabytes instead of the previous 45 megabytes of data. And of course it's adjustable by how many data you actually promote out. You can make it bigger or smaller depending on what you're actually interested in. And you can also define secondary indices here that you can see. I unfortunately, I think, have only 1 minute left, so I'm kind of coming now to the conclusion of the talk. Well, we already talked about the optimization hints. Secondary indices is basically just very simply identifying the path name that you want to specify. This one will be cost-based chosen. And what it basically is, it's basically just adding an is not null on the internal column that is being used for representing the value. Here are some interesting comparisons. We did some workload scenarios from customer workloads, one in the banking industry, one by life sciences, drug company, and an insurance company. And the size reduction that we achieved was between a factor of 3 to 200 on those particular data sizes in the index, for getting about between a factor of about 10 to 200 performance improvements. It depends, of course, on the query load, etc., but that's basically what you can kind of expect with that new thing to happen. And it depends all on the complexity, of course, of the data. Life sciences is probably less. It's more complex structured, more document-centric, while the insurance company was very relational in its nature. So the session takeaways. I think we have now an understanding when and how to use XML in SQL Server. We know how to write our XQuery methods and our XQuery expressions. And I think you have seen an insight into how we are going to evolve that in the future. I think we are over with the session. However, I'm more than happy to take any questions that you have, either now or later one-on-one or during the Ask the Expert sessions. Thank you very much. Thanks for your attention for the whole night here. Here's some additional information about white papers, forums, how you can contact me. And I would like you to basically go and provide feedback on the session. That session feedback is very important for us to be able to make improvements, especially if you can give us written feedback. I appreciate, of course, all 4s and 5s, especially the 5s. Don't please enter at once. I hate those. Okay, thank you very much for your attention, and have a great evening.